We'll go through the same set of steps here. Our next example will look a little bit more difficult. I'd like us to take a look at the expression 2x divided by x squared plus 1 squared dx. This is a much more complicated type of integral, but the beauty of the substitution technique is oftentimes it allows us to do things that look very ugly. We can often turn them into very straightforward problems that we can do. The first thing I need to do if I'm going to use the technique of substitution is determine where the composite function is in this particular problem. So I have to look for an inner function, and I have to look for an outer function. But you can see I have several different functions here. I have the 2x that's in the numerator. I have an x squared plus 1 in the denominator, and that's being squared. So there's actually several different things going on here. I have to think very carefully. Integration is not as easy as differentiation. There is an art to being able to see these. We will be doing many problems relating to integration so that you get a sense of what to do here. But my experience and instinct tells me I can see an inside function here. This x squared plus 1 is my inside function, and I can see an outside function here. I have this squaring going on, and that is my outside function. Notice that the 2x doesn't really enter into either one of those. It's not part of either of those things that I see, which may be a problem and maybe will not be. We'll have to see. Sometimes picking the correct values can make the difference between getting a problem right and getting a problem wrong. What I'm going to do now is the same thing that we did just a moment ago. I'm going to let u equal x squared plus 1. I'm going to let u equal the inside function in my expression. So u is equal to x squared plus 1. That's going to make the denominator very simple, right? That denominator now will look like 1 over u squared, which is something that we can actually find the antiderivative of. We can integrate that expression. The issue is I'm still left with a 2x, and I'm also still left with a dx. But again, something really cool happens. We need to relate du to dx. So I'm going to take the derivative of my substitution expression here. The derivative of x squared plus 1 looks like 2x. And so if I relate du to dx, what we find is that du is equal to 2x dx. And in substitution problems where you're expected to do substitution, this is a very common occurrence. This is a very common result for us to see here. And what I would like you to notice is that this 2x dx actually appears right here. So this integral has become quite a bit simple just by the work that we have done here. In fact, I can rewrite this as the integral of, in the denominator now, x squared plus 1 has become our u. So I can write this as a u squared on the bottom, and this 2x dx, this expression right here, is simply du. So this integral simply becomes the integral of 1 over u squared du. And this is a very straightforward integral that you should not have any difficulty with. It may be easier for you to solve this problem if we express this in terms of rational exponents instead, and write this as the integral of u to the minus 2 du. That may help you. Take a moment and do this integral, and maybe even then go ahead and substitute back in to find the result in terms of our original variable x. If you go ahead and compute this derivative, what we find is that we have minus u to the minus 1 plus a constant. This is the antiderivative of this expression, or another way to express this would be minus 1 over u plus a constant. And now we simply have to go back in and do our substitution. Recall that u was equal to x squared plus 1. So this expression then is minus 1 over x squared plus 1 plus a constant, and that is the integral of 2x dx over 2x plus 1 squared. So you can see here we ended up with a very straightforward integral that we had to do after making the substitution, because when we made the substitution, all of the correct pieces sort of canceled out and gave us a good result here. So that's a second example. The same technique typically holds with any kind of problem. And I want to finish this discussion with one last example from trigonometry. I would like us to take a look at the integral of sine of x cosine of x dx. This is a problem that is a little bit different, right? This is a problem that is not so clear-cut what is actually going on. And in fact, this doesn't even look like, right? This does not even look like a composite function. So I'm going to show you here an extension of the substitution method. I don't know a clear expression for the antiderivative of sine x cosine x. I don't, in my mind, have a good understanding of what that antiderivative would be. Maybe you do. It's not that difficult, and when you see the answer here, you're going to recognize that that is the correct result. But here we don't necessarily have a clear picture of what has a derivative of sine of x times cosine of x. So I'm going to go out on a limb, and I'm going to choose my u to be one of the trig functions. I'm going to choose my u to be sine of x. So what is my du dx? What is the derivative of u with respect to x? The derivative of sine is cosine. And so we find that our du is simply equal to the cosine of x dx. So we have now the pieces that we need. We have cosine x dx, that is our du, and we have sine of x, which is our u. So this is actually a very straightforward integral now, the way that we have expressed this. This turns into the integral of u du. So we're just taking the integral of a variable. This is going to give us 1/2 of u squared plus a constant. 1/2 of u squared plus a constant. If we recall, u was the sine function, so this gives us 1/2 of the sine squared of x plus a constant. This is the integral of sine of x cosine of x dx. This is a very straightforward problem to approach this way. It's not necessarily obvious that substitution is the best way to approach this problem, and there are other techniques that we'll learn later on that may help you to see what the right answer is here. But this does in fact work, and again, integrals are an art form, and you really need to gain experience with them in order to feel comfortable and confident in trying different techniques in order to solve a problem. So as a kind of a follow-up to this discussion, I would like you to do this exact same integral. I would like you to do the integral of sine of x cosine of x dx. And the only thing I'm going to tell you is that I want you to choose your u to be cosine of x. Okay? I made a choice to choose u, the u value in my integral, as the sine of x. But there's no reason to do that. Choose u equals cosine of x for your problem, and please show me that you get the same answer. This is also a good technique for exercising a little bit of work on your trig identities. So please show me that you get the same result. You get the same indefinite integral when you do this. And please have that prepared for the beginning of class next time we meet.